What is going on, guys? Welcome back to episode 3. So last time we talked about how to create these adders that can add any two number of bits together. And then we also talked about how subtraction is 2's complement. If you don't know what I'm talking about, please go check out that video. It will all make sense. It's part of a larger series that I'm doing. Now what we're going to do is we're going to see how we can select these bits together. Because I kind of talked about it at the end of the last episode. How do we actually tell the CPU which operations to perform? That, of course, has to do with the ALU, which is coming up in the next episode because it's such a big topic. This episode will be a quick one. We're just going to talk about two components. These are very interesting and important components that pretty much allow CPUs to work. And that, of course, is what NAND game calls the selector, but it's known to the industry as a multiplexer. So let's see what it does. A multiplexer basically says we get one bit that indicates which input is selected. So if S is 0, then D0 is selected. If S is 1, then D1 is selected. So the truth table shows exactly the same thing. Now let's build it. Again, pause the video if you want. Otherwise, here is the solution. So first, notice that we need to basically group these two together to S. And what gate does better than grouping stuff? Of course, that is the AND gate. So we need two AND gates. One groups S and D1 together, and then one groups S and D0 together. Now we have these two AND gates. Doesn't matter which one is correct, because it's just a selector. What gate doesn't care what matters or not? Of course, that's the OR gate. I don't know if that is probably poorly framed, but that is how I thought of it. So OR gate controls these two, and then we will connect this. Now, before I connect it, I know this will purposely fail because we're missing one important component. But let's see why. So we got most of these right. But for example, when S is 0, D1 is 0, and D0 is 1, let's replicate that. You can see S is 0, so that means D0 should go through. But why does it go through? Well, that's because you can see S is kind of binded to both of these AND gates, which means that S needs to be 1 for both of them to work, otherwise none of them will work. So clearly, these AND gates can't be connected together. What we need to do is we need to make them have complementary behavior. Basically, if one works, then the other. I mean, that's literally what a selector is, one or the other. So we need an inverter. And what we're just going to do is we're just going to place the inverter to any one of these AND gates, but I'm just going to place it here. Now connected to S, you can see all green check marks. That's because the inverter basically tells S you either go through this AND gate or that AND gate, not both. And then the OR gate still binds them together, and there you go. That is how a multiplexer works. So a multiplexer is pretty fun selecting things, but what we really want to do is what NAND game calls it switching. So switching is the opposite of selecting. You have one data component going in, and that feeds out to two channels. So, of course, just like multiplexer is called mux, this is what's known as a demux or a demultiplexer. So, it's just the opposite of what we did beforehand. And yeah, so see if you can figure it out. It's actually very similar to the last one. What we're going to do is we're just going to replicate the previous one, but just from the opposite direction. So remember, if you kind of vaguely remember, the OR gate is up here, then there's two AND gates, and then the inverter, stuff like that. But now the output's down here, and we still have this S, so we gotta be mindful of that. Now, we still need the two AND gates to control both of these. And then B goes to the data channel, and then A is a selector. But remember, we already learned our lesson. We need the inverter for both of these. Now, you might ask, where did the OR gate go? Well, take a notice. If you have two wires going into this input here, it already acts as an OR gate because the possible components are either 0 or 1. And with the OR gate's truth table, if they're both 1, then they're 1. If they're both 0, then they're 0. So we pretty much already replicated OR gate, what OR gate does, just by kind of like welding these two wires together. So that's the OR gate, how that works. The S still controls the complementary behavior. And guess what? We have two output channels. We have two AND gates. So it's as straightforward as you see. There we go. That is how you create a demux. Alright, so we've completed all levels in the switching. I know this is a short episode, but we're going to get ready for the next episode, which is the ALU. Think about how you can combine all the logic gates and all the adders to create some calculator. That is kind of like what you want to do in the next episode. So see you then.